So today we're going to talk about finding real zeros of polynomial functions. And so it turns out that a big part of the process for finding real zeros of polynomial functions actually involves the division of polynomial functions. And so we need to be familiar with the division algorithm for polynomials. Whoops. Which we are probably actually a little bit familiar with from the last section about rational functions, which says that if we have two polynomials, let's say p of x and q of x, and if we divide them by each other, right, that's equal to the quotient. Actually, instead of calling it, we'll call them f and g, otherwise it's going to be confusing. Let's call them f and g. So if I have two polynomial functions, f of x and g of x, the division of those is going to be equal to the quotient, which we'll call q of x, plus the remainder, which is also going to be some sort of function, over the divisor, which was g of x, right? Does not look like a q. Let's try that again. So the quotient, doesn't look like q either, really. So the quotient plus the remainder over the divisor. The divisor just was whatever was dividing the original polynomial function there. And we can write this in a different form. If we go ahead and we multiply the entire equation by g of x here, right, that will clear out this denominator and this denominator. And so we'll be left with the fact that f of x, the original polynomial itself, equals g of x times the quotient q of x plus the remainder. So both of these two statements are true, right? It turns out later on it's going to be helpful to sort of write the polynomial in this form right here. And of course, if the remainder is 0, if there is no remainder, then the polynomial is just equal to the divisor times the quotient, right? And so the fallout of this is if we find a polynomial g of x that divides f of x evenly, meaning there's no remainder, then if we know that g of x divides f of x evenly, then we know that f of x can be factored by writing it as a product of the divisor g of x that we picked and whatever the quotient is after we divide that out. And so we can use division, essentially, ultimately, to help us factor polynomials, right? So that's going to be big. We're going to use division to factor polynomials. Okay. So one of the important theorems that comes out of here. So we're going to go. We got to get a bunch of theorems down here. Polynomials tend to involve lots of theorems. And remainder theorem just says, well, let's go ahead and just say that so what it says is if f of x, just some polynomial, is divided, by the binomial x minus c, where c is just any number, then the remainder equals f of c. And we can prove this pretty easily. So first of all, let's go back to our division algorithm, which says that f of x, the second part of our division algorithm, equals q of x times g of x, which is the divisor, right, plus the remainder, right? So if we're dividing, let's think about this. If we're dividing my polynomial by x minus c, then what do we call x minus c? If we're dividing by x minus c is called the divisor. So q of x is really, in this case, x minus c, right, if we're dividing by that. Right? So what happens if you take f of c now? We plug in c for x. We get c minus c. Oops. Right? So we get c minus c times g of x plus r of c if I plug in c for x, right? And then what happens? The c minus c ends up canceling and becoming 0. So this whole thing goes to 0. And so we see that f of c ends up equaling the remainder, right? Which actually oh, and so one thing that's true that I didn't mention here is that we're dividing by x minus c, right? And so it turns out the remainder in instances like that is always just going to be a constant value. If we divide by like a first order binomial, my remainder always, because of the way division works, is going to be a constant. It's not going to be a polynomial itself. Sometimes the remainder can be a polynomial if we're dividing by a higher order, but my remainder can't be more than just a constant if I'm dividing by a first order, right? And so that means that it doesn't, if it's a constant, it doesn't actually depend on c, and so we can just say that we're just going to call it plus r. Whoops. I'm just going to call this plus r, plus r, plus r. So f of c ends up just equaling whatever the remainder happens to be, which is going to be a constant value. Okay. So that shows me that f of c is equal to the remainder if when I've divided the polynomial by x minus c, which you're looking at that saying, why is that important? Is that, why is that all that important? Well, and it's going to be a second before we can see that. But let's say I have the function f of x is equal to x cubed minus 4x squared minus 5. And let's say it is divided by x minus 3. So it's divided by x minus 3. What is the remainder? Right, okay, well, it's divided by x minus 3. What is the remainder? So if we use remainder theorem that we just established here, to find out the remainder, we can just take, if we want to find the remainder when it's divided by x minus 3, we can just take f of 3, and that should give us the remainder, right? So if we go ahead and evaluate that, right, we see we get 3 cubed, which is 27, minus 4 times 9, which is 36. 27 minus 36 is 9, minus is negative 9, minus 5 is negative 14. Okay. So to tell me that the remainder is negative 14, let's go ahead and just confirm that by doing polynomial long division here. So if we go ahead and divide this, x cubed minus 4x squared plus 0x minus 5. right? X goes into x cubed, x squared times. So we get x cubed minus 3x squared. And then we subtract, and we get negative x squared plus 0x minus 5. And then to get it to go into negative x, we multiply by negative x minus 3x. So if we subtract negative 3x, we get positive 3x. We drop down to negative 5. Then lastly, we have to multiply the whole thing by 3 to get it to go into 3x minus 5. And we end up with negative 5 minus negative 9. We're adding 9 is really going to give us 4. What did I do wrong there? So we see we made a mistake here. We get it back up. That should be plus 3 right there. Negative 3 times negative x is plus 3x. So I should have negative 3 right here, which means I have to, right here, multiply by negative 3. All right? And so that will mean I'll get negative 3x plus 9, which will give me negative 14. So I'm subtracting 9 from negative 5. So we've shown that this is indeed true. So if all I have to do is find the remainder, this is a much easier method than polynomial long division, as has been perfectly well displayed right here. So remainder theorem can be very useful for finding the remainder if you have to do that, which oftentimes you do. So the next theorem, which is probably the most important theorem that we're going to learn today, factor theorem is important because it's going to allow us to solve polynomial equations through this whole division process that I was talking about before. And that says that if f is a polynomial function, right, x minus c is a factor of f, if and only if f of c equals 0. What does the if and only if part tell me here, geometry people? If and only if means this is what type of statement? It's a special. It means something different than just regular old if by itself, right? It's called a biconditional statement, right? What does that mean? It's biconditional. It's an if-then statement. Whoops, I put an extra if in there. No, I didn't. Never mind. That was supposed to be there. Just didn't underline it. So what does that mean? Biconditional. Sorry. Then, there should have been a then in here. Sorry, then x minus c is a factor of f if and only if f of c is equal to 0. So we have an if-then statement. If f is a polynomial function, then x minus c is a factor of f and only if f of c is equal to 0. If and only if indicates that it's a biconditional statement, which means that you can read it in either direction. So if f of c equals 0, it follows also that x minus c must be a factor. If x minus c is a factor, it's true that f of c has to be 0. So you can go in either direction. Right? If you know that x minus c is a factor, then you can conclude that f of c is equal to 0. If you know that f of c is equal to 0, you can then conclude that x minus c is a factor. Right? So either of those two facts leads to the other. And that's important because that's not true for a lot of theorems, right? Just because one thing doesn't always imply the other thing just because it worked the other way around, right? But this one does in this case. And so to prove that it's a biconditional, we have to prove both statements, but we're just going to prove one of them. So the proof is this, and it's a pretty easy. The reason we're doing these proofs is because they're pretty easy proofs to do. So let's suppose, whoops. Let us suppose that f of c is equal to 0. So we're starting off with the fact that f of c equals 0, right? So by the division algorithm, f of x, if we divide it by x minus c, is equal to x minus c times q of x plus f of c. Why am I adding f of c there? Why am I putting f of c there? What did the remainder theorem tell us? That if I divide by x minus c, the remainder is f of c. So I'm saying my original polynomial is equal to the divisor, right, times the quotient plus the remainder. It just happens because the remainder theorem, f of c is the remainder if I divide by x minus c. So that's why instead of saying plus r, I can just say f of c, because the remainder theorem established those are the same thing. So we need remainder theorem to prove this here. That's really important. Now, if that's the case, right, we just said a second ago that f of c is equal to 0, right? So we end up getting that, right, f of x is just equal to x minus c times q of x. And isn't that the definition of x minus c being a factor of q of x? Right? If f of x is equal to x minus c times some other polynomial, q of x, then x minus c is a factor. So we've just shown there that if f of c equals 0, that means x minus c must be a factor. And by a similar proof, we'd show that if x minus c is a factor of the polynomial, that means f of c is equal to 0. That means that if x minus c is a factor, that means c is a 0. What is the graphical implication of a 0?
X-intercept.
It's an x-intercept. So we can find x-intercepts of a graph where f of c equals 0, right, by finding a factor, by finding factors, I should say, of the original polynomial f of x right here. Okay. So we can use factor theorem. So is x minus 1 a factor of the function f of x equals 2x cubed minus x squared plus 2x minus 3. So is x minus 1 a factor of that polynomial? And then you can answer the same question about x plus 2. Is x plus 2 a factor? Okay, so if we want to figure out if x minus 1 is a factor of f of x, then we can just take f of 1, and we'll get 2 times 1 cubed minus 1 squared plus 2 times 1 minus 3, and we'll end up getting 2 minus 1 is 1, plus 2 is 3, minus 3 is 0. So x minus 1 is a factor, right? Because the remainder is 0. And lastly, is x plus 2 a factor? Well, we have to take f of negative 2 by our theorem, right? And that'll give us 2 times negative 2 cubed minus negative 2 squared plus 2 times negative 2 minus 3. And so we'll get 2 times negative 8 is going to be negative 16. Negative 16 minus 4 is going to be negative 20. Minus another 4 is going to be negative 24. Minus 3 is negative 27. So that one is not going to work, and so x plus 2 is not a factor. And so the whole point of this, like I said before, is determining whether x minus 1 is a factor, or x plus 2 whether it's a factor. And the whole point of that is to ultimately be able to factor out this polynomial, because we don't really have methods for factoring, or so far we don't have methods for factoring a lot of higher order polynomials like these ones right here. Like, we didn't know how to do that before. So how can we use this fact to factor this polynomial right here? Well, it turns out we're going to have to employ some long division. And so because we're going to be doing a lot of long division in this section, we're going to learn a new type of polynomial long division called synthetic division that makes it a lot faster. And so knowing that x minus 1 is a factor is great, but unless we know what it factors out into, okay, so this factors out into x minus 1 times something, right? So this equals x minus 1 times something. We have to know what that something is to fully factor the polynomial. And that's where the division comes into play. Because that something is the quotient when you take this and divide it by this, right? Then we get the quotient plus the remainder over the divisor. And so this times the quotient of dividing this by this is what this is equal to, based on the division algorithm. So let's take this same example here, and we're going to use long division, synthetic division actually, to figure out what this has to be multiplied by to equal the original polynomial right here. So if I have the polynomial f of x equals 2x cubed minus x squared plus 2x minus 3, and I know that x minus 1 is a factor. So I want to fully factor f of x if x minus 1 is a factor. Which we know it is. We just checked it out. So instead of using polynomial long division, where we go ahead and with polynomial long division it would look like this. We'd set it up like so. Right? Instead of using polynomial long division, we're going to use what's called synthetic division, because it's faster. Synthetic division is essentially designed for when you're dividing by a binomial. And so synthetic division only works when you're dividing by a binomial like x minus 1. If I was dividing by like a quadratic or any higher order polynomial, I can't use synthetic division. So in synthetic division, what I do is I put whatever this number is right here, and if this is negative, we're going to put, just like, you know how with our remainder theorem, or with our factor theorem, sorry, if x minus c is a factor, then f of c is equal to 0. So the important number was c if this is negative. We're going to look at this if this is negative, then we're looking at positive 1 here. Because if x minus 1 is a factor, then positive 1 is a 0 of the polynomial, right? So if 1 is a 0, then in synthetic division form, we're going to set it up like this, right? And then we're going to go, and then over here, we're going to put all of the coefficients of, instead of actually writing out the whole thing, this is how we're saving time, we're only going to put the coefficients of f of x here. So that was 2, the next coefficient was negative 1, and then 2, and then negative 3, right? And we realize what happens here, right, and then we're going to put this down here. And often I don't even write this part. Usually I just write it like this. Right? And so what we're going to do here, well, we'll put the top bar just to, why not, is let's just follow the first couple steps of this, this long division here. If I wanted to do the long division over here, right, I do, okay, well, x has to be multiplied by 2x squared, right, to become 2x cubed. And so x times 2x squared gives me 2x cubed minus 2x squared, right? And what we end up doing here is the 2's cancel, right? And then we do negative x squared minus negative 2x squared, so we're adding 2x squared, so we get positive x squared there. And then we just drop down the plus 2x minus 3, right? And then for the next one, x times x gives me x squared. Negative 1 times x gives me negative x. And then I subtract again, and I get positive 3x, and drop down to 3. And then lastly, I have to multiply by 3, and I get 3x minus 3 and my 0 remainder, which is what I was expecting, right? And so this is one way to do it, but we see this is a pretty long process. It involves writing a lot of stuff out, and we'd like to sort of shorten this if we can, because we're going to be doing a lot of dividing by binomials like this, and this is a quicker way of doing that. So regular polynomial division, and this is the quotient, right? So x minus 1 times this equals this by the division algorithm, and that's always true. This times this equals this, right? Unless we have a remainder, in which case it's this times this plus the remainder equals the original one. But if the remainder is 0, then the divisor times the quotient always equals the the dividend in those cases. So what we're going to do here is in synthetic division, we're going to realize that ultimately all I'm doing is I end up just, and in synthetic division, in addition to only dividing by binomials, we're only going to divide by binomials where the coefficient is 1 on the first term. So right here, x minus 1, the coefficient is 1. So because this coefficient is 1, I just end up multiplying by whatever the coefficients of, in each case I multiply by 2, then I multiply by 1, then I multiply by 3, and then I'm multiplying by whatever the coefficients are essentially. So what I'm going to do here is I'm going to drop down the 2. So I always take that first, in synthetic division, I always drop it down. And then that 1 had to get multiplied by that 2, right? So 1 times 2 is 2, and the 2 goes right there. And then we have, just like we have this right here, don't we? Negative 1 minus 2, except what we do here is because there's no negative here, we just add, which means there's no subtraction, which is nicer as well. And so if we just add these, we get 1, which, here's my 1 right here, right? And here's my 1 right here, right? So I get the 1 that I got from that as well. And so then I do that process again. Because the coefficient on this was 1, I have to multiply the whole thing by 1x here. So I do 1 times 1, and then I put that right there, and then I add those, and lo and behold, I get my 3 right here for the same exact reason, right? And then this spot right here is always the spot for the remainder, right? So if the synthetic division went well, and we should get a 0 right here, right? And so then the last thing we do is we do 1 times 3 is 3, and then we add those together, we get 0. So there's no subtraction, it's all addition. We only deal with the coefficients. We don't have to worry about any of this other stuff. And so you can see that this involves a lot less writing, and it's a lot quicker than this process. And it's the same we're not doing a different process. It's just that when we know that the only thing we're going to be dividing by is like x minus some number or x plus some number, we can greatly simplify this process because there's so many things that are the exact same in each one of these processes when we divide by a binomial that's this simple. Right? So once again, this works only for a divisor of the form x minus c. We can cut out all of this extra stuff here because we know we're only dividing by a divisor like this one right here. It's the only reason we can do that. Otherwise, we would have to do the full polynomial long division. Okay. So we're going to use synthetic division from now on to do these types of problems. And so the whole question, okay, well, what's the point of that? Well, the point of that is now I can say that the polynomial 2x cubed minus x squared plus 2x minus 3 is equal to the divisor, which was x minus 1, right? Times what our quotient was, which if we looked there, ended up being 2x squared minus x
Plus x.
Was it plus? Yeah, plus x plus 3, right? So now the next step would be to go ahead and finish by factoring this quadratic right here, right? And then we'd have something times something times. So we want to fully factor it. So we have a linear times a quadratic. Now, is this quadratic factorable? They won't always be. can use fishbowl, right? So factors of 2 are 1 and 2, and 2 and 1. Factors of 3 are 1 and 3. We're looking for a sum of 1, which we can't get. So this quadratic is prime, meaning that is the fully factored form. Right? That's the fully factored form. So you guys should probably go and practice that now. So let me give you an example that, to work on here. So if it is a factor, I don't know. I'm going to have you guys go ahead and do an example on your own. Take the polynomial f of x equals 3x to the fourth. So sorry about the break there. So if we have the polynomial 3x to the fourth minus 6x cubed minus 5x plus 10, show that x minus 2 is a factor. And fully factor f. All right, so go ahead and give that a crack. Okay, so to show that's a factor and to fully factor it, we're just going to go ahead and, instead of using the factor theorem and taking f of 2, which would tell us whether x minus 2 is a factor, we know that if it is a factor, it's implied that it is a factor, so we're going to use synthetic division so that we immediately get whatever the quotient is, so we can use that to factor f of x afterwards. So we're going to just go right to the synthetic division. So if we're trying to divide by x minus 2, then we're going to put in our synthetic division as positive 2, right? And then we're going to put all of the coefficients, 3, negative 6. And notice we're missing an x squared term here. In synthetic division, you have to have a placeholder. So if we're missing a term, that means, sorry, let me fix that really quick. That means we have to put in a 0 for the x squared term that is not there, and then we can put the negative 5 and then the positive 10. So first thing we always do is drop down the first coefficient, and then we do 2 times 3, which is going to give us 6, and then we add. Negative 6 and 6 is 0. All right, so then 2 times 0 gives me 0, and then we add those two zeros together, and we get another 0, right? And then 2 times 0 again is 0. Negative 5 and 0 is negative 5. 2 times negative 5 is negative 10, and lo and behold, we get 0 in our remainder place, and so we have confirmed here that x minus 2 is a factor, because when I divide by x minus 2, I get a remainder of 0. We also have the quotient here. This gives us the quotient. So now that we have all these places here, it's important to know which is which. So this is called, the quotient we get here is called the depressed polynomial. Right? And the first coefficient or term of this is going to be 1 lower power, or and an easier way to put this, probably a better way to put this, is that the depressed polynomial is 1 order lower than the original. All right, meaning that because this was a 4th order polynomial right here, the depressed polynomial is going to be 3rd order, and this is going to be the cubic term, this will be the squared term, this will be the linear term, and this will be the constant term. So what I'll get here is that means f of x is going to be equal to x minus 2 times the depressed polynomial, which is the quotient, which is 3x cubed minus 5. Right? And it turns out that 3x cubed minus 5 is prime. It's not factorable. And so that is the fully factored form now of this polynomial. And we know the whole reason we want to factor this is if we want to find the zeros of this polynomial, we're going to set it equal to 0 and then solve each of these. So we know if x minus 2 is a factor, 2 is a 0. If 3x cubed minus 5 is a factor, then we can set this equal to 0, right? And we could, if we wanted to find the other 0, we'd go ahead and set 3x to the cube minus 5 equal to 0, and we would get that x is equal to the cube root of 5/3, right? So we found another one of the zeros right there. Right? So it turns out that there are only 2 real zeros for this particular guy right here. So we have 2 zeros. One of them is 2. The other is cube root of 5/3. Right? This is a fourth order polynomial. So it turns out this is going to have 4 total real solutions, but it only has, 4 total solutions of any type. It only has 2 real solutions though, which is interesting. We'll talk a little bit more about that in a second. But that does lead us into this next idea. This is just a theorem, which is a polynomial function of degree n has at most n real zeros. It doesn't have to have all n real zeros. It could have fewer than n real zeros, but it has to have no more than n real zeros. So a fourth order polynomial can have no more than 3 real zeros. A quadratic, we know from experience, can only have 2 real zeros. It could also have 2 complex zeros. It can have no real zeros theoretically, but it can have at most 2. So the order of the polynomial is the maximum number of real zeros that the polynomial could have. And those zeros correspond to the x-intercepts of the graph. We know that some polynomial functions have not as many, right? So we'll leave off on that for a second here, and then we'll take a break. The question now becomes, so we have this new theorem, which sort of makes sense based on our observations in the past about quadratics and the cubics that we've seen so far. But we also just saw a fourth order polynomial that only had 2 real zeros. So we know that they don't have to have exactly n real zeros, but a polynomial function of degree n can have no more than n real zeros. It can certainly have less. So the next question is, well, this remainder and factor theorem is great and all, but unless I actually have a factor to test, how can I actually use it to solve a polynomial equation? So for instance, if I have the polynomial equation f of x equals 2x cubed plus 11x squared minus 7x minus 6, and I ask you to go ahead and solve this, well, where would you even start? I mean, you know, if you know one of the factors, you can divide it off and figure out what the depressed polynomial is and finish factoring it. But if I asked you to just go ahead and fully factor this, I didn't tell you any of that stuff, how would you even begin? What would you just, I mean, you would just be left guessing, picking random numbers in the hopes that one of them is 0, and you just divide and divide and divide until you found one that worked, which doesn't seem like a very good strategy. So what we want to do is we want to have a theorem that will help us narrow the possible real zeros that we can test, so we don't have to test an infinite number. We can test just ones that are possibilities. And so that's what the next theorem is going to help us do, the rational zeros theorem. Right? And it says, if we have a polynomial function, f of x, which is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1, just the general form for a polynomial, plus a to the 1 x plus a naught. So we have some polynomial function of some degree, of some order, we don't know what it is, where each coefficient is an integer. So the a sub n minus 1, all of the a's are integers. So where each coefficient is an integer. Whoops. So backing up for a second here. We have this polynomial, and all of the coefficients, each of the coefficients is an integer for this polynomial. If that's true, if P over Q in lowest terms is a 0 of f, then P must be a factor of a naught. And Q must be a factor of a sub n. So this is a really interesting theorem. It says that essentially what we're saying here is that all of the real zeros of this polynomial have to be of the form P over Q, where P is a factor of a sub naught, whatever the constant is, and Q is a factor of a sub n, whatever the coefficient on the highest order term is. So what we can do, we can use this fact to construct possible real zeros for our polynomial by taking all the possible combinations of factors of a naught and factors of a sub n, and putting them and mixing them together into fractions. All right. So going back to that previous example, to use this rational zeros theorem, solve the polynomial f of x equals 2x cubed plus 11x squared minus 7x minus 6. Right, what we're going to do is we're going to use that theorem to come up with possible real zeros for this polynomial. And the factor that theorem, the real zeros theorem, essentially restricts the possible real zeros that we could have. So what we're going to do is, first of all, let's find all the different factors of P, or what P could be, and what all the different possible values Q could be. And so P, the numerator of our real zero, has to be a factor of 6. So what are all the factors of 6? What do we got? 1, 2, 3, and 6, right? And that each of them can be plus minus. Right? And factors of Q, plus or minus 1 and plus or minus 2. All right, so we want to go ahead and construct all the possible P over Q's that we can, and these would represent all the possible zeros of this particular function. So if Q, so Q is the denominator, right? If Q is 1, then 1, 2, 3, and 6 would all be possible real zeros, plus or minus. And if 2 happened to be the denominator, right? If 2 is my denominator, then I can have 1 over 2, 2 over 2, 3 over 2, and 6 over 2, right? So I could have plus or minus 1/2, plus or minus 2/2, which is just 1. So we already did those, so we don't have to list any repeats here. Plus or minus 3/2, and plus or minus 6/2. Well, or 6/2 is just 3. Right, and we already had 3 right here, so we don't have to list that. So these are all the possible zeros. So if there are any, if there are any real zeros of this polynomial, they have to be one of these. Right, so we've reduced the number of possible zeros that we can test. And so what we're going to do now is we're going to use synthetic division to determine which ones of these work and which ones of these do not work. All right, and so we're going to use an even more, and so since we're going to be testing a whole bunch of different possible zeros, we're going to need to use an even more compact form of synthetic division. right? So normally with synthetic division, let's say, let's just try doing 1, right? So let's say I wanted to test to see if is 1 a real 0, right? Let's say positive 1, is that a real 0? So we do 1, right, and then we do all our coefficients, 2, 11, negative 7, and negative 6, right? Drop down the 2, 1 times 2 is 2, 11 and 2 is 13, 1 times 13 is 13, 13 and negative 7 is 6, 1 times 6 is 6, and lo and behold, I got lucky there, and I picked one that actually is a 0 because it has a remainder of 0, right? So as always, we're looking for this remainder to be 0, and if it is, then we know that 1 is one of my zeros there. Okay. Now, let's say that I didn't get lucky on the first try. Another way I can set up my synthetic division to allow me to test a whole bunch at once. So let's go ahead and say that I'm going to test some ones that don't work. Let's say I'm going to test negative 1. Let's say for some reason, usually we start with the smallest possible zeros, right? That are whole numbers, and we start with the positives just to make it easier. But let's say I went a different direction. I wanted to test all these right here, right? So I can use this other form. This is also just synthetic division, but what we're doing here is we're going to just sort of write out less of it, but still do the same thing. So in this form, what I've done here is on my left here, these are all the zeros I'm testing. I want to test negative 1, negative 2, negative 3, and 6, right? And so what I'm going to do is on top here is where instead of the coefficients going here, the coefficients are going to go up here. 2, 11, negative 7, and 6, right? And so what I'm going to do is the first row, we know I just dropped down the first coefficient, right? And so this whole row in the middle here is not going to exist anymore, right? We're going to have to just keep that part in our head. So we only have this part, and what's going to go right here is just this right here, right? So this part is going to go right here, this part is going to go right here, and this part is no longer going to exist. It's just going to be in our head. So we're going to say, okay, well the next thing we have to do is go 2 we have to go negative 1, right, times 2 gives us negative 2, and then we have to add that to 11, right? So negative 1 times 2 is negative 2, plus 11 is 9. And then we're going to go negative 1 times 9 is negative 9, and negative 7 is negative 16. Right. And lastly, negative 1 times negative 16 is positive 16, and 6 gives me 22. And so the remainder is not 0. Whoops. Just going to try and line this up a little better. That's actually lined up pretty well. And so the remainder is not 0. And so we know that negative 1 is not a factor. And we can keep going ahead, and so we can keep going and testing negative 2 and negative 3, and then all the way down to negative 6. So why don't you guys go ahead and finish filling this out, right? Test negative 2, test negative 3, and test negative 6. See if any of them work. And of course, we're always looking at the end here to see if we have any remainders of 0, which are would be the ones that would work right here. Yes, and remember, you could actually just fill your whole first row in here. Your whole first row is just going to be all 2, right? Because you always drop down the first coefficient, whatever it is, when you're dividing by a binomial that has a coefficient of 1 on the first term. All right, let's go ahead here and finish this whole synthetic division grid, if you will. So starting the second line here, we're going to go negative 2 times 2 gives me negative 4. Negative 4 and 11 will give me 7. Right? Negative 2 and 7 is negative 14, and negative 7 is negative 21. And negative 2 and negative 21 is positive 42, and negative 6, which is going to give me positive 36. So that's not a real 0 because the remainder is not 0, right? The next one, negative 3 times 2, will give me negative 6, and 11 is going to be positive 5. Negative 3 and 5 is negative 15, and negative 7 is negative 22. Negative 3 and negative 22 is positive 66, and negative 6 is 60, so that's definitely not a factor. And then negative 6. Negative 6 times 2 is negative 12. And 11 is negative 1. Negative 6 and negative 1 is positive 6 and 7. Or sorry, negative 7 is negative 1. And then we get negative 6 times negative 1 is positive 6 and negative 6, which is 0. So this one is a factor. So negative 6 worked. So you see that goes pretty fast when you set it up that way. You can test a lot of zeros in pretty rapid succession if you use this sort of setup for your synthetic division here. And you can just sort of check them off here. Like I said, I usually start with the smaller numbers. I'd start with 1, negative 1, 2, negative 2, 3, negative 3. And I would definitely do the fractions last. Okay. And hopefully the goal is you only need to find one, especially with a cubic. Once you've found the first one, your depressed polynomial is a quadratic, and you can find the last two zeros by looking at the depressed quadratic there, using either quadratic formula or by factoring the quadratic. So you only have to find one. You didn't have to find the 6 and the 1. If you found the 1 or the negative 6, you're good there. And so the next step then is, let's say I found the 1 first, and so I said, okay, here's my depressed polynomial, which if I found the negative 6, here would be my depressed polynomial, right? And so that means that I can factor this out as x minus 1, right, times 2x squared plus 13x plus 6, right? So that's what f of x is equal to if I factor out the x minus 1. And I can find the remaining two zeros by factoring this quadratic right here. So let's go ahead and do that on the next page. Whoops. So we have x minus 1 times, what was it? It was 2x squared
plus 13x
plus 13x
plus 6.
plus 6. So that's what I factored f of x out into. And so now I'm going to go ahead and try and factor out the 2x squared plus 13x plus 6 part. I'll just go ahead and use a little fishbowl for that. Right, and so I'm looking for a sum of 13. 6 and 2. 3 times 2 is 6 and 2. Seeing that. So the one that works is 2 times 6 is 12, and 1 times 1 is 1 for a sum of 13 here. And so this will factor out to x and 2x, and the 2 has to multiply the 6, and the 1 has to multiply the 2. Or the 1, rather, yeah. And they're both positive. So there we go. So now I fully factored that polynomial. And the zeros of that function, the x-intercepts, are going to be, that means 1, 1, negative 6, and negative 1/2. So those are my 3 zeros. Those are the 3 x-intercepts of that polynomial that I found by using the real zeros theorem and polynomial long division. All right, and we're going to call it quits there because we're in our time, and that should pretty much give you all that you need to be able to do the homework for tonight. So the assignment for tonight is the following. So here's the assignment for tonight. The first part, this comes from the new handout, the 4.5 stuff. And this is from yesterday's handout, this other stuff right here. All right, so that's it. Have a great day.